Greetings, everyone. I'm Laura McNealy, and my focus this summer has been high-entropy alloys. But first, I want to give a huge thank you to my mentors, Dr. Ryan Baumbach, Dr. Kyle Way, and William Lucas Nelson. So first, let's try to tackle what high-entropy alloys are. They are a new class of material that has potential to revolutionize biomaterials as we know them. With further research, these alloys could be the key to finding a complete replacement for the human bone and joint, which is a huge step for technology. A good material to serve in the body, as we know, has to be safe, it has to be strong, resistant to corrosion, and ductile. This search has been ongoing, as it is difficult to find a material that cooperates with the body while keeping its integrity and safety. High-entropy alloys are a new discovered metal by mixing 5 or more metals together, compared to a normal alloy that is mostly composed of just one. This composition sets high-entropy alloys apart, giving way to chemical disorder, structural order, and impressive strength and superconductivity. My team decided to make 4 different alloys and test their properties. In order to make these alloys, we use a method called arc melting. This heats up the elements in an argon atmosphere, and when heated, they form into a bowl as shown to the right. With all these alloys made, we are now finding out their general and magnetic properties. The X-ray diffraction data shown here shows us the phases and impurities in an alloy containing titanium, aluminum, nickel, silicon, and vanadium. The black points that you can see here have many peaks showing the constructive scattering of the X-rays on the crystalline lattice, while the theoretical data is shown in red. This data also shows us the distances of these planes compared to theoretical expectations, which is shown in green here, the bluish green color. As you can see, there's multiple green peaks, which shows that this data shows that it has a high entropy alloy phase as well as another physical phase present. We'll have to do more research to understand why these peaks are here and what other properties this alloy has. We also tested the magnetic accessibility of the alloy, and that's basically just how strong spins are in material when they respond to a magnetic field. So a cartoon of what this is shown to the right. In a paramagnetic material, the spins are disordered, but they line up and have a larger magnetic response when you have a applied force. What we want from a good biomaterial is a non-magnetic material with small spins and a small response. This is the case for the alloys shown to the left, as the magnetic accessibility is small and there's a low temperature dependence. We can conclude that this material is non-magnetic and is a potential effective biomaterial. We have been successful in finding the magnetic properties for a high-entropy alloy, but the next steps are to find other properties of it, including its strength and how it may react with the human body. For time, I went over 1 alloy that we made, but we actually made 3 others. Doing further analysis will help us understand the properties of these high-entropy alloys and their potential role in technology.